Business Weekly conducted a survey of graduates from 30 top MBA programs. On the basis of the survey, assume the mean annual salary for graduates is 10 years after graduation is $137,000. Assume the standard deviation is $33,000. Suppose you take a simple random sample of 76 graduates. Find the probability that a single randomly selected salary is at least $131,000. So we can't technically answer this question using normal distributions because we weren't really told that the original population was normal to begin with. And it's probably not even safe to assume that given, the way salaries work. But the essence of this particular problem wants us to understand what's happening with the central limit theorem. So that's why they're not telling us what's happened, that this is normal. But that's okay. We'll go ahead and answer it as is. And so, assuming that this is a normally distributed set of data, it would have the mean given of $137,000 and the standard deviation of $33,000. The mean is right in the center, 137,000, and then 131,000 is somewhere lower than that. And I want the probability that x is greater than this, so I'd shade to the right. And to find my probability, I'm going to use the normal CDF function because that gives me normal probabilities under the normal distributions curve. And it takes 4 inputs. The first 2 inputs are the lower and upper bounds of your shaded region, which I've used e to the 99th in place of positive infinity. So that's just something very large. It just means 1 times 10 to the 99th power. The last 2 inputs are the mean and standard deviation of your distribution. Oops, I need another 3 in there. There we go. Now, using the calculator, I'm going to run the normal CDF function to find this probability. So second distributions, normal CDF, 131,000. Then second e with 99 gives me e to the 99th power. 137,000 and 33,000. So that is 0.5721. So that's the area under the curve that I'm interested in. Now, you may have seen a menu show up when you did the normal CDF function, and that's okay. Some of the later model calculators have that. Just to show you what that is, if I go under normal CDF with those turned on, in my case, it's just the same 4 inputs, but it gives you the ability to type those in a menu so that you don't have to remember what the inputs are or what order they go in. So it's just to help you. So if you have them, it's nice, but if you don't have them, it's not essential. The problem can still be solved. In fact, it just takes those numbers and plugs them into normal CDF for you. So either way is fine. Okay. Next, it says to find the probability that a sample of size 76 is randomly selected. And you want to know the probability that the mean of that sample is at least $131,000. So we're now comparing what happens when we invoke the central limit theorem. So that's what is meant when we bring in a sample of items. When we have a sample of items and we're trying to find the probabilities there, the central limit theorem guarantees that the sampling distribution, so if we pull multiple samples out of our population, now I can't write and talk at the same time. So if we take multiple samples of size 76 out of our population, take the average of those samples and put those into a frequency distribution and plot it, that's going to form a normally distributed set of data. So that sampling distribution is normal. So even though the original population wasn't specified that it was normally distributed, we can still be guaranteed that the sampling distribution of a set of samples are, as long as those samples are larger than 30. The mean and standard deviation of our sampling distribution, we have to come up with those. What's nice is that the mean is unaffected. So the mean of the sampling distribution is the same as the mean of the population. The standard deviation, however, is reduced by a factor, oops, too many zeros there, by a factor of the square root of the sample size that we're drawing. So when I take that into account, that's going to affect my probability. We'll see how that happens in just a moment, but for now I'm going to just show you that none of the inputs here have really changed much. We're still working with normally distributed sets of data. We're still shading to the right. We're still using the point of interest of 131,000. So the only thing that is changed is our standard deviation. So the lower bound of the shaded region is 131,000. The upper bound is positive infinity still. The mean is 137,000, but the standard deviation is 33,000 divided by the square root of 76. When I go to put that in the calculator, second distributions, normal CDF, it's actually really nice when you have these menus because you can see everything on screen a little bit easier. And since I've already typed most of this in, all I would have to do is put the square root of 76 onto the last one, or divided by the square root of 76, that is. Then when I hit paste, it'll put it right into the normal CDF function, and I'll get my answer. So 0.9435. If you don't have those menus, that's okay as well. It still works just the same. It's just a little bit more effort in typing in those values. So if you have them written to the side, that's extremely helpful. So 131,000, second e to the 99th, my next input. 137,000 is the mean. 33,000 divided by the square root of 76. And there we get the exact same answer, 0.9435.